Hi, thank you very much for coming to my talk today. My name is Takashi Ikegami. I'm from University of Tokyo. I'm very happy to present my talk today because I have been working in complex system sciences for more than 25 years now. So I'm very happy to present my recent research on entire tracking and then also large-scale swarm experiment. Let me tell you a little bit about the history of complex systems from my personal point of view. 1990, there was the personal computer has been very much available, and then also the internet has launched in 90s, right? So that time, the artificial life conference was started in Los Alamos in 1987, and then I think around this time, complex system studies has also launched. And then at this time, we have basically we have computational tools, which is cell automata, coupled map lattice, and also coupled oscillator lattices. These are the very simple systems, but show some temporal oscillation, temporal chaos, so that when they are coupling together, there's a very interesting emergent phenomena popping up from there, right? So this is how, especially computer scientists and physicists got interested in sort of complex systems, and then started to work on this one. Then we have 2010, and now we are in 2020. So I say that 2010 is a very revolutionary era. So I say. In many aspects. One is, I think around this time, there is the people say about the life log, and also big data. And then personally, I found this year was a very special year because, for example, like Rubik's Cube was solved that even from the worst configuration, initial configurations, you can get to the solution, which the color is aligned, is 20 moves. This was proved using thousands of Google computers and then nice optimal optical optimizations. And then also there are zebrafish, starting from the 64 cell stages to the almost entire fish form. They are taking three-dimensional laser slices and get nice movies, so that you don't have to make approximations to these developmental processes, but you can just see what happens actually, which cell goes to where, and how they differentiate. And these are the big, to me, was a big changes from 2009 to 2011, right? And also, I must say there is a Boids speech home project. Well, this one is when he got his own baby, he put audio devices and visual devices in his house and recording his son's movement for up to 3 years. So without parents looking at him, this data tells you how the baby got walk around and gradually acquiring language. And from analyzing all this entire data, that he says, okay, the language acquisition is not going on in his own brain, but entire house layout and where and when the parents is moving around, that is everything is a factor for organizing this language acquisition machine. So, and besides this, we have we have an iPhone, we have a blockchain, and of course we have deep learning. And every impressive event has happened around this year. So I say this is a revolutionary year. And since this year, I think what we see now is around this early stage of our complex systems, we say this is a small model plus storytelling. But now we have a large model plus, I say, it's more like it's a natural history. Like description of much data flow. So my standing point of research has been shifted from a small model plus storytelling to large model plus natural history description of the large data set. So I'm going to talk about what that do I mean here, right? And that's, I think, it's a very revolutionary changes, because what we know here is that quantity changes quality beyond certain level, and then also we can understand the collective behavior without human biases, human cognitive biases, which I think is very important. And so now we can start up a new complex systems, and we are looking for a new theory, new mathematics, which is account for this crazy era. So today I'm going to talk about two topics. One is it's called the entire tracking experiment. And the second thing is large scale the model. These two topics, I have to again, I have to remind you that after 2010, it's going to be main two topics of the complex system studies, not just small models plus storytelling, but we have to think about the large-scale model and the entire tracking, and a new kind of data analysis is coming up now. Okay, now the first topic, which is the entire tracking experiment. So as I said, I'm collaborating with Jane Robinson's group, which is at the University of Illinois Urbana-Champaign. And they're using 1,000 bee workers with one queen, and making artificial one-day honeybee hive and recording 24 hours for 7 days. And each bee is detected by a QR code on his back, so that it's interesting that we call it bee code. So we know that like a B557 is what he does on this day at this time, what at this time. So you see, this is an interesting video recording of how the bee it does. You know, so white triangle is that's corresponding to bee's position, and then triangle is heading direction of the bee. So when there's a white line is coming up, this means that bee is interacting with other bee face to face, and which people call it trophaceous interactions. And what we notice watching this video is that sometimes the honeybee hive, entire honeybee hive becomes so busy, so excited. Then it's calmed down, and again excited. And what this one is, so I asked Jane Robinson and other colleagues, but they didn't notice. So we try to look into this bursting behavior and see whether that does something to do bees hive functions and other things. And this global excitation is called global bursting. This is here's a time series of how the birth is happening as time goes by. And when you are scaling up, like this 2012 July, that you can see like spikes goes up. What do I mean by spike is computing kinetic energy, how busy the bee is moving around, and then summing up all the individuals and see how this amount changes over time. So, as I said, each bee has its bee code that we can track all the bees, and when this guy got excited and is calmed down, and the other one goes up and get depressed again. So we see that how the individual activities committing to the entire activities and all this kind of stuff. And then also, as the honeybee is famous for its dancing in the numeral 8 shape, so that we also have detected this dancing action. So basically, in order to characterize this honeybee dynamics, we have a kinetic energy time series and the trophaceous time series, dancing durations, and then also when the bee is out of the scene, out of the video, that we say, okay, this bee goes out, and then after a while they come back, because this artificial, even if this is artificial one-layer hive, there's a door open to the actual environment. So they go out and then come back. So the first 2 days, the door was closed. And then after 2 days, the door was open so that bees can freely going out and then coming back. Sometimes it's not coming back, but when they come back, then they do something and then again, the bees go out. So it's more sort of a pseudo-natural phenomenon that we can see in the wild honeybee. Okay, so there are several observations that we found from this analysis. First one is when the guys are coming back from outside, as people say, that bee sometimes do dancing, right? So the dancing behavior is triggers this kinetic energy, I mean, the big bursting behavior. So the big excitement it seems like triggered by the dancing behaviors. And then big dancing behavior, big excitement is also triggers next going outside actions. So there's this interesting chain of reactions. Coming back from outside, dancing, and then big excitement, then that triggers bees to go out. So we use like a non-negative matrix factorization to see what is this pioneer bees, which triggers the big exciting behaviors. We call it pioneer bees. The pioneer bee is just a extracted excitation mode of the first kind in this bursting behavior. Like this one, I can see that if you have a burst, like 42 agents got excited first, and that seemed to trigger other 900 50 bees to excite. So we call it pioneer bees. And you see the pioneer bees that, first of all, there's a 44 bees got excited. Then afterwards, after like 1,000 seconds, then the big burst is coming up. So machine learning tells you that there is a set of group, which is pioneer bees, that can excite, that can trigger the global excitement. And then those pioneer bees always include the dancers. So dancers are also the pioneer bees. The dancers can excite, can trigger the global excitement. The second thing is that who is the pioneer bees? That's the big question, right? I know that dancers is the member of the pioneer bees, but the pioneer bees is what? It is just an artifact of the machine learning. Maybe so, but we didn't think in that way. Maybe there's a biological meaning of pioneer bees. So we characterize each bee, each burst, by who is the pioneer bee of the burst. So if it's one, if this burst and this burst has the same pioneer bees, then we say these bursting event is closer to each other. But if they have a different pioneer bees, different set of pioneer bees cause this burst, then they say it's separated, right? So we plotted on the 2D space using multidimensional scaling, so that the bursting behavior is changing in this 2D space. The red one is before the entrance opens, and then after door opens, then this burst is moving in this 2D space in anti-clockwise way. So it's very clear from this figure that starting from the blue set, the pioneer bees is rather randomly selected, then gradually moving towards the left lower corner means that the bees honeybee hive is also developed, and then they seem to have a common pioneer bees. So the pioneer bees are converging into South Hudson set, and then as you see on the right, on the right, so the red ones burst with waggle dancing is proceeded. Therefore, it's sort of maturation of the honeybee hive. First of all, there's no dancers, just the bursts. But then the dancers is gradually coming up, and then the pioneer bees, the roles of pioneer bees are fixed. So the same members of the bees seem to compose the pioneer bees and bursting behaviors. So as you can see that before the door opens, there's no foragers because the door was closed. And when your door opened, there's a foragers, and after a while, and then dancer emerges. But still, we don't know what's the pioneer bees are. So this one is an interesting picture that the red one that is coming up now, right? And it's surrounded by the green ones. So the green ones is called dance followers. There are people studying dance followers, and they have actually they are decoding the information carried by the dancers. So dance followers is another division of labor of this beehive. And then we detected that like 64% of the, or almost 70% of the dance followers are the pioneer bees. And then there's a top-down causation by measured by the transfer entropy, but we will skip here. So we can simply summarize here, right? So I think multidimensional scaling in terms of pioneer bees, that there is a maturation of honeybee hive, and the members of the pioneer bees seems like it's dance followers. It's gradually converging into the same set, which I think is interesting. And then also the burst occurs spontaneously without being followed by the waggle dancers. So even if without dancers, if there's no dancers, still the bursting behavior happens. But the proper dancers coming out from outside, then there's a dance floor was become pioneer bees and causing big excitement in the entire hive, and that triggers the next bees to go out. So that's a chain of reaction that we put as a number 4. So I think it is very, for the first time, it is systematically detected this chain of reactions in the beehive, and then maturation or self-organization of the beehive dynamics. Because there's a spontaneous activation of the bees dynamics, it looks like a brain systems that spontaneous activation is going on, and that is maybe is very important for preparing for the proper foragers to come back from the outside and to distribute information carried by the dancers. I mean, but by the foragers. Okay, so we move to the second topic, which is a large-scale swarm experiment, and in maybe that you have seen this the famous starling swarming with each other. It's a huge numbers of starling you can see, even in Tokyo also, that you can see starling is moving and making a big swarms. And this one, but interestingly, these big swarms are also interacting with each other, it seems like. So we want to understand what happens in not just a small size swarming, but the large size swarming behavior, if we can understand computationally generated, and what we can understand here. But the big question is, what is the flocking? What is the swarming behavior? Because the swarming behavior is that maybe locally that the agent is aligning their heading directions, but it's not that kind of flocking. Or maybe like a mosquito is just making aggregating behaviors. So that's another flocking behaviors. So the big check, the famous definition of flock is measuring alignment of heading directions. And then he defined this big check, what we call a big check order parameter, by summing up all the heading directions as a vector, right? And then taking absolute value of it, then you can see if this order parameter is non-zero, that there's a order emerges, and this alignment order is the sign of flocking behavior. But of course, there is another different types of definitions, like spatially connected or informationally connected, or maybe something like a functionally connected. So we are looking for another types of definition of flocking and swarming behaviors. And our model is the computation model is based on the Craig Reynolds' original model, which was proposed in 1987. This model does consist of 3 basic rules. One is attraction. The other one is alignment of heading directions. Then the third one is repulsion from the others. Linearly adding those terms, we can realize what's the Craig's ideas of flocking behavior. And we used Newtonian equations for doing this. See how this number of the scale matters using this model. For example, once the numbers of agent is small enough, like 256, we only have like a tolerancing behavior like this one, depending on parameters, of course. But this is the typical behaviors of the swarms of the small size. Then we scale up the numbers of the agents 20 to the 11th numbers. This is the periodic boundary conditions for the 3D case. So in this case, the swarm is making a big trail and just going straight in this case. But for the 2 to the 15th, that you see some different types of swarms emerges, which is like a big bulb that you can see on. It's connected from the right to the left boundary. So there's one big bulb. But up to the 2 to the 18th, as you can see, different types of blobs emerges, and then each blob has sticking out those strings from the surface. And now we're up to like 2 to the 19th. Then it's a very but entire picture that you can see when you have a size of 1 million boids. The behavior is complex enough and a good example of self-organization. So I can show you some of the longer time video. Here you can see almost a million boids, is 500,000 boids is moving around and gradually forming swarming behaviors and flux. What we notice here is that slowly the blob, like a big blob swarm, is formed, and also there's a strain of boids moving into the same directions. And then it's gradually the network structures, or what we call a rhizome structure, is formulated. Means that the big blob, randomly moving big blob aggregated swarm is connected with the strain of the agents, the boids moving into the same directions. So this network structure is characteristics of a large-scale Boid model. So you see this large-scale Boid model shows some very interesting phenomena. So we look into a little bit the details of what this rhizome structure tells us. First of all, we clustered and tried to detect each individual swarms, but it's difficult. So first of all, we use a DBSCAN to show how spatially connected ones can be a candidate of the flocking behavior. And interestingly, that you can detect a different speed, different behavior can be detected even in the same flocking behaviors. On the left, that you can see the blue ones are slowly moving agents, but on the surface of the blue one, that there's a fast agent is moving. So it's a natural divisions of labels of slowly moving swarms and fast moving swarms. And the fast ones are more coherent movement, and then slower ones are more randomly interacting with each other. So in this video that you can see, the violet color is a small slow agents swarming behavior, and the red one is a fast speed moving agents. And you see these red ones are connecting big blob ones, violet swarms. And then also on the surface of the blob, that there is a red ones is moving on the surface. So that's something. It's swarming behavior, but it's speed does matter for defining the flocking behaviors and swarming behaviors. Okay, so coming back to the slide, that there's two peaks in the distribution of speed of the swarm. One is in the middle, the other one is the very slow ones. And then as we saw in the last movie, that the slow one is the big ones, and then fast one is the small string ones. And then we also computed the fluctuations of this Boid. The horizontal line is the size of the swarm. And you see the smaller ones, the fluctuations has the fluctuations in terms of the velocity, but the larger ones has the fluctuations in the local density. So the kinds of fluctuation changes once we change when we see the different size of the swarms. So when this fluctuation is different, it has a different responses to the external perturbations, as the statistical mechanics tells us. So that's interesting that even if with the same rule set, but the emergent swarming behavior has a different kinds, and at least from this fluctuation perspectives. And you see, if you have only the same speed that exists in the swarm model, means this parameter mu equals to 0, then there is only simple aligned swarming behavior emerges, which is Vic-check order parameter is non-zero. But once we have a distribution of velocities, then we have about like aggregated behavior emerges. So there is a phase transition by changing the bound of the velocities. And then there's a transition from the non-zero Vic-check order parameter swarms to aggregation behavior, which is Vic-check order parameter is 0. And then we also measure the transfer entropy, and then there is a top-down causation from the swarms to the individual agents. And summing up, so we think this is a very interesting behavior we could observe, which is related to superorganisms proposed by Brad and Wilson. As I said, there's a rhizome structures, which is non-zero Vic-check order parameter non-zero bulbs is connected with others through fast-moving agents. So each bulb is cannot survive independently. They can only survive by interacting with others. But once we can interact with others through this fast stream of agents, then they can survive. But there is a finite lifetime. Gradually, they are decaying out. So it's not the underlying agent, but the collective swarms has a finite ages, and then survives for a while by interacting with each other. So this, if we take a bulb as a one single individual, they can interact with other individuals through different interactions. This time is a first strain of agents is a way to interact with other swarms. So even if the swarming, the underlying void has a very limited interaction kinds, but on top of it, in the level of swarms, new type of interaction emerges, which is first strain of agents, stream of agents, which I think is emergence of next layer in the swarms. So, but summing up, that the maybe not only spatially connected, but the same speed, same directions is important to extract swarming structures from this model. And then I said the small flux has a velocity fluctuations, but the large flux has density fluctuations. And then when the flux emerges, there's a top-down causation emerges, which I didn't have time to talk about. But also this, I can call it the superorganisms because in the kinds of interaction is different. Underlying agents, that interaction is like attractive, repulsive, and also alignment. But at the level of the swarm interaction is mediated by the first stream of agents, which is the emergence of superorganisms. And then next superorganism on top of this swarm is probably up to like 1 billion or something. That's what we are exploring right now, because taking each big swarm as one particle, and then on top of those assembly of particles, that we can expect meta swarming behavior emerges on top of it. Okay, so let me summarize what we discussed today. So back in 1990, that we have a small model, then we have a storytelling to explain what is brain, what is evolution, what is collective behaviors. And the human observer can extract patterns, should extract patterns, and also human observer produces those small models, and also storytelling by simulating those models, what the equations. But after 30 years, now, particularly after 2010, our way of doing science, I think, has becomes very different. First of all, we have a massive data set, massive data flow, so that small model cannot have its proper reality. So we have to shift to a large model like GPT-3 or Alpha 14.2. These are the good examples of the large scale models. And then we can't extract patterns because the data set is so huge. So the machine learning can extract patterns instead of human observers. But still the question is how we can understand the system. Even if the machine learning can extract patterns, we do have to interact with the machines. So one of the things that I can think of is that maybe machines should make different kinds of stories, which is not human biased, but it's more like different types of stories and narratives that we are expecting for. Maybe they are not written in natural language, but maybe it's a new kind of mathematics. But what I'm hoping for is to have storytelling machines instead of storytelling by ourselves, which is, I think it's waiting for us in the future of complex system sciences. And one of the examples is like how to automatize a scientist, not scientific experiment, but the scientist's activities. What the scientists think of should be automatized with techniques of machine learnings and deep learning and some other things is coming up in the future. So I'm very excited that the new era of complex systems is now open, and maybe 10 years from now, I do hope a new storytelling about the evolutions, new storytelling about the brain science will coming out from complex system sciences. Okay, finally, let me introduce my collaborators. This is my team from my lab, working in HoneyBees, Boids simulations, and also Tetrahymena collective behaviors. I didn't have time to introduce this, but they are very working hard every day to help me to develop this new era of complex systems. Thank you very much.
Okay, very nice. So, thank you very much, Takashi, for the recorded lecture. Let me check a minute. There is several questions here now, if you can see. So we have a few minutes that you can answer these questions. Do you read them, or should I read them for you?
Okay, yeah, please.
Can you read them?
Which one? It's
on the chat, in the chat, sir.
Yes. So I think I answered some of the questions was written on the chat.
Is there any question that you have? You can turn on your microphone and you can ask now. We have a few minutes.
how much do
How much
that's,
do you need to explore parameters to get interesting patterns is the question there.
that's a very interesting question. I think Hiroki, you have a bunch of intuition to choose a good parameter set. So we had a longer time to find out which in between, you know, like spherical clusters and then also streams of flocking behaviors. So on the edge, there is some interesting swarming behavior emerges. So that's we did manually to find out, but maybe we have to do some systematic way to find out the good parameter set to show some interesting complex behaviors.
Okay. What is the time necessary to define a superorganism?
Yeah, that's also a good question. So these big swarms can only exist by interacting with other swarms. So there is a finite time life, finite lifespan, as I said, that's gradually decaying out. But so I didn't see any sort of a long-lasting swarms. It's always, you know, decaying out. But also, if we extract one big swarm, and it's suddenly, it's almost immediately, you know, collapsing, decaying out. So maybe this is interaction with other swarms by using those strains of swarms can coexist between those swarms. So it's very important to have this new kind of interaction between large swarms and large swarms because they are communicating. That's why they can coexist. So that's the lifespan is also computed from this one. The superorganism related to the pseudo particle in physics. Yeah, I thought maybe because when I was working with the oil droplet, which is moving around, it's active matters. And then sometimes they are making aggregations and making a big ensembles. And then the lifetime is different from the individual oil droplets and also the big ensembles of the droplets. So it's pretty much like this one. So a pseudo particle in physics, in that sense, is related. It is yeah, maybe it's actually. So we are also analyzing big web services. In the web services, there is implicit, you know, community is emerging. So we can extract those social groupings from the data. So after like 2-3 years of social services, and then we got the entire data from the company, and then we extracted some groups. Also, you know, the users or subscribers didn't notice they are belonging to this group or other group. Suddenly, you know, certainly we can see those societies. So it's like you know, like a big swarms in our simulations, and those human community is like swarms, and they are interacting with each other, and then they can sustain its structures. So you're right. So this is also applicable to human society and in human crowd, and they once just, you know, increase the size, then there is a spontaneous speciation, spontaneous differentiation can happen, so that you can see divisions of a labor is for free. So that's, I think, is the interesting point.
Okay,
yes,
very
so
good.
Humans can, yes.
Very good. Are there any other questions before we quit? The next is the break. So you have time now to ask some other question.
So there's one from Mihai Petrov that he says the human being cannot exist itself isolated. He needs communication with each other. Healthy state also is defined by the communication, social communication stuff. But this is true. So even the bees, and then, you know, Boids model, and then also web data, they are always interacting with each other, and this interaction can let the the big macro scales to come out, and then social differentiation is also possible by the communication. But also that's why they can coexist with each other. And the other question is, are these interactions modeled using modular networks? I haven't tried that. I think it's an interesting idea. And then, yeah, maybe so. We try to make a phylogenetic tree of this social data. Then you can see some of the main phylogenetic tree and other trees, and then you can see some series of inheritance of the phylogenes. This is also true for the Tetrahymena. So once we have a collective behaviors of Tetrahymena, one individual is divided into 2, and then also divided into 4 and 8 and 16. And then there is a nice, the speciation of the globes. So one of those phylogenetic tree, the partial phylogenetic tree, is good at doing something, but the other one is doing something else. So even though it's starting from the same genetic single clone cell, but it's without any mutations, but because of the interaction with each other, there is some sort of differentiation can happen in the community, which I thought was interesting.
Okay, one last question. I see Takashi here. Are there interactions modeled using modular networks?
Yeah, I already answered that. So I think it's a good idea, but I couldn't. I didn't do that. And then the last question is maybe can you use this?
The last one from can you use the appearance?
Yes. To simplify the model. Represent system that contains large numbers of individuals using a small numbers of super. Yeah, well, that's so. This is more like a spontaneous renormalizing particles or the agents, right? And then so you can go up to like 2-3 different orders, then so that you can see those swarms as a particle, and then again there's another swarms we expect to come up. So I think it's an interesting idea, and then I want to use it to simplify. It's like a natural renormalization is going on in this computational Boids model, but still it's on the way. So if I can succeed in doing this, I will write a paper.
Okay, great. Thank you very much. Thank you very much.
Thank you so much for attending my talk.
Problems that are very much in the heart of complex systems, and I'm glad there is such a nice interest from the community. We have to stop now to get a few minutes of break because we start soon in the parallel sessions. So in 5 minutes, actually, we break to the 6 parallel sessions. And in this room will be parallel session number 1. And there's another 5 rooms, which you all have the links. All the links are online in the website, which, by the way, is open. So we break now and meet in a few minutes with parallel sessions.